Here we're going to take a look at the rationalization technique. Now this is a technique for evaluating the limit of a certain class of functions. And as we see later on, we'll use this technique to evaluate the derivative of some common functions like the square root of x. So let's start with this example. We want to evaluate the limit as x approaches 0 of the square root of x plus 1 minus 1 divided by x. Now let's see what happens first if we plug 0 in for x. Let's see what we get. Well, if we put 0 in for x, notice that we get the square root of 1 minus 1 divided by 0, and that of course is 0 over 0. Now when we get that, that means that this limit may exist, so we have to do some further analysis on it. So what we're going to do to evaluate this is the following. There are two common math tricks in mathematics that you see used a lot. Sometimes you'll add something in and subtract it right back out. You use that when you complete the square or when you prove the quadratic formula. And then there's another math trick when you multiply something in and divide out by the same thing. That's what we're going to do here. So what we're going to do with this limit is we're going to multiply by what we call the conjugate of the numerator, the square root of x plus 1. And all we're going to do is change the sign of this negative right here. We're going to make it positive. And then we're going to divide by the same thing. Okay. This is called the rationalization technique when we do this. Now, we'll see how it works. Now, what we're going to do from here now is we're going to FOIL out the top and we're going to multiply the denominators, but we're not going to actually FOIL out the denominators or distribute the x in. We're just going to leave them be. Now, also notice here, when we do this, when we multiply by this term over this term, we haven't changed anything here, right? Because these two terms cancel and just give us back 1, right? So we haven't really changed anything. Now, when we FOIL this out, when we FOIL out the numerators, what we get is so root x plus 1 times root x plus 1, that's going to give me x plus 1. Now notice that when I go root x plus 1 times 1 plus negative 1 times root x plus 1, those are going to cancel. Now I'll write them out this one time just to show you that they cancel. You see the first one we're going to get is root x plus 1. That's root x plus 1 times 1. And then minus 1 times root x plus 1. And then minus 1. Okay, that's coming from negative 1 times 1. Alright, then in the denominator, we're just going to write it as x times the square root x plus 1 plus 1. And we don't want to distribute the denominator. We don't want to distribute that x in. We just want to leave it alone. Now notice in the top up here, of course, like I said, those two middle terms in our FOIL method cancel. Notice that this negative 1 cancels with this one over here, and what we're left with then is the limit as x approaches 0 of x divided by x times the square root of x plus 1 plus 1. Alright, now notice what we have here now is these x's cancel, which is good because that's what was giving us trouble over here. Because x was going to 0, the denominator was going to 0, so that's what was giving us trouble. So we were able now to cancel it out. And what we finally end up with is the limit x converges to 0 of 1 over square root x plus 1 plus 1. And now we can just plug that 0 in for the x here. And there's no trouble. We have no trouble plugging that in because we're not going to be dividing by 0. And we end up with 1 over root 1 plus 1, which is 1/2. And that's our answer. That's what the limit is. Okay, so this technique is called the rationalization technique. Now we have a graphic down here. Illustrating this problem. The blue curve right here, that's the graph of the root x plus 1 minus 1 over x. Notice you have a little hole right here where when x is 0 down here, because this is undefined when x is equal to 0. Right here is x. The black dot right here is f of x, and notice as x approaches 0, that black dot right there, the f of x, is going to approach 1/2. That's 0.5 right there. Right there, that's 0.5 on the y-axis. Okay, and so you see as x is approaching 0, f of x, which is the square root x plus 1 minus 1 over x, is approaching 1/2 from either side. Okay. All right, so let's take a look at another example down here. And if you'd like, with these examples, you can always try these on your own. You can pause the video, try it on your own. So with this one here, we're looking at the limit as x approaches 3 of this quantity. Well, let's see what happens if we try to plug 3 in for x right away. Well, if we put 3 in for the x, well, what we get here is a square root of 9 minus 3 divided by, of course, 3 minus 3, and, well, yep, we're getting 0 over 0. Okay, so that indicates that this limit may exist, and let's try the rationalization technique, because after all, we see this square root right here minus a number right here. That is a giveaway for the rationalization technique. So what we're going to do is we're going to multiply by and divide by the same thing. Okay, so this is just the conjugate of the numerator here, and then we're going to FOIL out the numerator and just multiply x minus 3 times the denominator, but we're not going to FOIL anything there, and this becomes alright. Now when I multiply out the numerators, square root x plus 6 times square root of x plus 6, that just gives me x plus 6. Now, of course, root x plus 6 times 3 will cancel with root x plus 6 times negative 3, so I'm not even going to write them out. And then the final term is going to be negative 3 times 3. That's going to be minus 9. Divided by x minus 3 times the square root x plus 6 plus 3. Now notice what we have in the top here. This is x plus 3 in the top, right? 6 minus 9. I'm sorry, negative 3. 6 minus 9. So the top is x minus 3. X minus 3. And so that cancels with this x minus 3 down here, leaving 1 and 1. And that's typical for the rationalization technique. You see the part over here that was giving you trouble, because it was going to 0 as x was going to 3. when we apply the rationalization technique, it cancels. That's typically what's going to happen. So you end up with the limit x approaches 3 of 1 divided by root x plus 6 plus 3. Now we can plug this 3 in for the x right here. There's no problem doing that. We won't be dividing by 0 when we do that. And we end up with 1 over the square root of 9, which is of course 3, plus 3, and we get 1/6. And that's our answer. All right, let's try one more. Okay, now I would encourage you to try this one on your own. So, assuming that you've done that, I'm going to go over the answer now. So let's check out here. If I put 1 in for x, what we get is the square root of 2 minus the square root of 2. So that's 0 over 0. Yep, okay. So looks like this has a chance to exist, and we see a square root minus a number in the numerator. That's an indication of the rationalization technique. So what we're going to multiply top and bottom by plus right there. We want a plus. Okay, so just the conjugate of the numerator there. All right, now when I FOIL out the numerator, what we're going to get is limit x approaches 1. I'm going to get x plus 1 and then of course the two middle terms here are going to cancel. Root x plus 1 times root 2, negative root 2 times root x plus 1, they will cancel, and then negative root 2 times root 2 is going to give me minus 2. All of that over x minus 1 times the square root x plus 1 plus root 2. Okay. Now of course the top here is x minus 1. 1 minus 2, that's negative 1. So this x minus 1 will cancel with this x minus 1. And we end up with the limit x converges to 1 of 1 divided by root x plus 1 plus root 2. Now we can plug the 1 in for x. No problem, not dividing by 0. And we end up with 1 over 2 root 2. And that's our answer. If you'd like, you can get the radical out of the denominator by multiply the top and bottom by root 2 over root 2. And you would end up with root 2 over 4. All right, that's what you get when you multiply top and bottom by the square root of 2 to remove the radical from the denominator. And that's your answer. You can leave it like that, or like this is fine. Okay. All right. So that concludes our discussion about the rationalization technique.